home on the range. Okay, so once again, we're talking about that road by Chick-fil-A that only my students actually understand what it is. Um, but in our last problem, we had a dip going like this, and we were, in the car. In this problem here, we're actually going to crest over the hill. And this causes our stomach to kind of like rise up into our throat. We kind of feel like if we went any faster, we'd be launched into orbit, like, pew, we're gone. So let's look at one of these centripetal force problems where we're going over the hill. If I could ever draw it, there it is. And how fast would we have to travel? So what's our velocity here, rather our speed? Would we have to travel to feel weightless? And remember, weightless means that our normal force is equal to 0. Well, if we draw a picture, because Grandpappy Bossler told us to always draw a picture, and if you haven't been drawing pictures, then what would you be doing with your life? Here's our car, top of the hill. We know we have a weight acting down on it. We know that the weight equals mg. And because we're sitting in the car, something has to push back on us. There is a normal force here. And just like always, we want the center of the circle, or things acting in that direction, to be positive, and things acting away from the circle to be negative in this case. So if we set up our sum of the forces equals ma, and in this case, our sum of the forces will become a centripetal force, which equals a mass times a centripetal acceleration, we are going to have here our positive weight, plus a negative normal force, so minus n, and this will be equal to m times the centripetal acceleration, which is v squared over r. If we want to start actually trying to solve for this here, we know in this problem, we're looking for the speed, and we want to find that speed such that the normal force equals 0. So we could actually just plug in 0 to this problem. And what this allows us to do, is just to say that the weight, mg, equals mv squared over r. This is actually really, really cool. We've started to see this a little bit in our physics class, but we're starting to see that the mass doesn't actually matter. Small car, big car, who cares? The mass means nothing. What does matter here is what is gravity here on Earth, and what's the radius of your actual arc. If we were to continue this circle around, that kind of looks like a bad circle. What's the actual radius here? If we go from the center out, our radius in this case is approximated as 40 meters, and that's all that matters. So if we solve for v here, we can multiply each side by r, so that we'll have rg equals v squared. And then just to get rid of that square, we'll take a square root of each side, which gives us our final answer of velocity equaling the square root of 40 times 9.8. And whatever that number is what we want. 40 times 9.8 gives us, 392, and then we take the square root of it. Gives us about 19.8 meters per second. And it's a speed, so it's just meters per second. So that's part A in the problem. That is what we were looking for. Here's our answer up here. So we did that problem correctly. Feel good about that. If we flip this problem, kind of like we did in the notes, if this was a dip instead of a traveling over the hill, how heavy would we feel? Well, if you recall that, if we wanted to redraw the whole picture, always a good idea to do so. The weight's acting out, which is negative, and the normal's acting up, which is positive. And if we recall that equation from our previous setup, we're actually going to get the normal force equals the mass times gravity plus v squared over r. We derived this equation in our last video with this exact setup here. So if we wanted to figure out how heavy you'd feel, we can just put everything in this case. The mass is 700 kilograms. Gravity is 9.8 meters per second. The velocity from the last problem was 19.8 meters per second, which we will be squaring, and then we'll divide that by 40. As we go to throw things into our calculator, one of the first things that I like to do is figure out what this is. And whenever you throw that into the calculator, 19.8 squared divided by 40, you actually find that this number is 9.8. And what we have here is 9.8 plus 9.8. We sometimes in the world of physics, depending on what you're talking about, we scale things in terms of how many gravities is that, how many Earth gravities. So this is like 2g. So you're going to be like twice as heavy. You're not experiencing just one Earth's worth of gravity, but two of them. So if we take the 700 kilograms and multiply it by that, you're not just going to experience, mg. It's like m times 2g in this case. So if we take 700 and multiply it by 9.8 and multiply it by 2, we get a total normal force of 13,720 newtons. So you would feel twice as heavy. And this is actually something, talking about G's like this, it's often talked about in like Air Force pilots. They're going through like a turn or they're going through a dip and they're pulling 6 G's while doing that. The act of like pulling G's is centripetal force idea, and it's like all of a sudden you have artificially created 6 times normal gravity, and it's just because that centripetal force is pushing back on you with this amount. So sometimes pilots can pull 8, 9, 10, 11, 12 G's of force or of acceleration in this case, and that means that if they're going to feel 12 times as heavy. So if you weighed 200 pounds, all of a sudden you now weigh, what would that be? 2,400 pounds, something like that. If you went 12 G's, it got a little bit heavier. So they have all sorts of advanced things that they use to do that. But this problem now is finished. Adios, and you all take it easy.